So there, we saw that pressing the hiccup alarm call activated hiccup neuron, its respective place in the dentate gyrus, and its position within the CA3 place cells of the hippocampus. And this sent out recurrent connections to all of signals across all of its recurrent axons and dendrites to all other neurons in the CA3 region of the hippocampus. But the signal wasn't strong enough on its own to generate a strengthening of the synaptic connections with other neurons, because the other neurons themselves weren't activated. Now, if you remember what I was saying about the long-term potentiation Hebbian plasticity diagram, if this neuron fires, but this neuron hasn't had an increase in its voltage already, it hasn't been activated enough by this neuron, it consequently won't fire, and it won't reach an increased voltage on the inside of its membrane here, enough to knock out the magnesium ion out of the NMDA receptor, and as a result calcium won't come in and activate CAMK2, which will cause a nucleus to increase the number of AMPA receptors, which means that if just one neuron in this network fires, whilst it sends out a signal to all of the other neurons, it isn't strong enough to increase the connective weights it has to those other neurons. So I'll do it again. Hiccup alarm call. Watch it for it sending the signal. But because these other neurons aren't already firing, it's not enough to make them have a causal relationship between this neuron firing and another neuron firing in the network. Another good example would be Felid. Say if the capuchin sees a Felid. In this case, Felid neuron here synapses with this region of the dentate gyrus and consequently this region of CA3 of the hippocampus. As you saw there, that sent out signals, but because there was no other event, it didn't become linked to any other event. It did generate a predator escape response, as we would expect from previous videos that I've done to demonstrate how Capuchi-Net works. Now, however, now we should be seeing that Capuchi-Net, if it's given two events within close succession, it should be able to link those two events using this artificial hippocampus. A natural scenario for a black-tufted capuchin would be that it hears a hiccup alarm call from a conspecific, another capuchin. It doesn't know what that means, but then soon after it sees a predator like a leopard, a felid. It could be a puma, and because it's in close succession, that is enough to knock out the NMDA, to knock out the magnesium out of that NMDA receptor and increase the connection between felid and hiccup alarm call. There should be a link between the two, particularly if this scenario where the felid and the hiccup have been paired is repeated. I'm going to demonstrate this visually now. So we'll have felid alarm call, and then I'll follow it up by pressing the activation for the felid representation. Watch these neurons. There, you see they fired an extra time, and that's the Hebbian rule, the Hebbian plasticity. Neurons that fired together, wired together, and because they all these neurons send recurrent connections, they caused each other to fire, and then each other caused each other to fire, like a feedback. I'll reset the dynamics and demonstrate the principle again. So that's feeled. Oh, sorry, that's the hiccup alarm call. We now press feeled. Watching. There. They should usually only fire once. By themselves, they only fire once. But if we pair them together, they begin to increase the connectivity between each other. This neuron and this neuron begin to increase the strength of their connection and thus cause each other to fire twice. There. And that's the equivalent of if this neuron fires, this neuron now fires. So now we've officially, in the CA3 region of the hippocampus at least, caused hiccup alarm call to initiate the representation of feeled. Now remember when I was talking about the hippocampus, I mentioned how the hippocampus begins to fire up again when the animal's in sleep. And this eventually sends a signal back up into the cortex and causes cortical regions of the cortex to fire up together and wire together. And this is because CA3 connects to another region called CA1, cornu ammonis 1, which then feeds back up via the subiculum and entorhinal cortex back into the cortex. I've hidden them from this display. We'll now put them back in.